Okay, today we'll begin our study of simple harmonic motion. So what is simple harmonic motion? Simple harmonic motion is motion caused by a linear restoring force. The force, in other words, has to be proportional to the displacement. And it's not affected by the amplitude, in other words, how far it's displaced from its equilibrium position. It will continue forever if there's no friction. And some examples that we'll be studying are like pendulums or mass on a spring systems. All right, I'm going to revisit Hooke's law. The deformation of an object is proportional to the force causing it. There we have an equation. Force is equal to minus kx. So for example, if we take a block and we push it from position 1 to position 2, compressing a spring, we apply a force, and this is a linear restoring force. In other words, the spring wants to push it back out. How much it wants to push it back out depends on how far we pushed it in. So the more we push it in, the greater the force to push it back out. The negative sign indicates that when you push the block to the left, the spring wants to push it back to the right. So the force is in the opposite direction of the displacement. And K is the spring constant, and the spring constant is measured in newtons per meter. In other words, how much force you need every meter to either stretch or compress the spring. And X is the displacement, and that's measured in meters. This is a linear restoring force because it actually falls into the category of, or in the format of, y is equal to mx. Y is equal to mx plus b actually, but there's no y-intercept in this case. So F is like y, and K is the slope, and X is x. So it does fall in their linear format. All right. Hooke's law. The restoring force of an ideal spring is negative kx. Now I alluded to that before a little bit, but let's say we take this ball. Well, first of all, let's say this is the unrestrained position. In other words, there's no force acting on it when it's just hanging out in this position on this dotted line. And we take it and we pull it outwards. Now the spring wants to pull it back in. So that's why you pulled it out, and the spring wants to pull it back in the opposite direction. So there has to be a negative sign. Okay. Let's look at an example. The spring constant of a spring, in this case, is 320 newtons per meter, and the bar indicator extends 2 centimeters. What force does the air in the tire apply to the spring? So in other words, we have like one of these air pressure gauges. We hook it up to the tire. The air leaves the tire a little bit and pushes down on the spring, compressing it. How much it compresses it would tell you how much pressure is in the tire. So what we're looking for is what force does the air in the tire apply to the spring? So we know how far it moved, and we know the spring constant. So we know the force applied is equal to kx. I ignored the idea of the negative sign in this case, and we were able to figure out how much force was needed to push it out that distance. Okay, here's another interesting problem. This is more of a conceptual problem. You have a 10-coil spring, spring constant K. The spring is cut in half, so there's 2 5-coil springs. What is the spring constant in each of the smaller springs? Okay. Well, the whole spring, looking at the top here, when it's compressed x distance with a force F applied. Okay. Now, if you take the spring and you cut it in half, the 2 halves actually still have to compress x distance, but each of them will only compress half that distance. So this half of it will do half the distance. This distance will do half of x as well. And the force throughout the whole spring has to be the same because of Newton's third law. For example, let's say where we cut it in half here. This part of the spring here is pushing on this part of the spring here. By Newton's third law, this part of the spring here has pushed back with the same amount of force. So the force is the same throughout the whole thing. But each half of the spring is only compressed half the distance. Therefore, so for the same force applied to this little spring here, which is half the spring, it only moved half the distance, so therefore the spring constant is double for the half the spring than for the full spring. So let me see if we can understand that logic again. This had a spring constant based on the idea of F applied at distance x. Well, this still has the same F, but it's only moving in half the distance, so the spring constant must be double.